we'll now take questions from the audience.
I'm Subhash Mehrotra, past president consulting engineers India and member of the FIDIC board. My questions, two questions, one to Mr. William Baker and another to Mr. Jang. Mr. William Baker, the height of the approximately is 800 meter. So under wind, what is the top lateral deflection? And as for the top deflection under wind, and at the residential level, what is the deflection? Because even if we go by height by 500, which normally the codes provide, for the 800, about 1.6 meter is the permissible. And even if I consider mid-height, 400 meter, the permissible is almost 0.8 meter. Is it a comfort level deflection? Because I have felt only 10 mm deflection and I was not comfortable. So this is a question to you. To Mr. Jang, the question is, you have provided flat plate. In the residential and the earthquake, how do you cater for the ductility and ensuring that with the response reduction factor 5, it will not punch through? Thank you.
Okay, let me make a shot at that. Okay, but when we get into very tall buildings, we don't pay as much attention to deflections as we do as to accelerations, and more importantly, the rate of change of accelerations. We always look at them. We always look at our movements, but they're no longer. We never longer use them necessarily as controlling criteria. We try not to get out too far from norm or the like. The actual movement at the top occupied floor is in the order of a little bit less than a meter under a storm that happens once in 500 years, or 50 years, sorry, once in 50 years. The building is actually, it's interesting because you got to think about how do you perceive motion? You perceive it through your body inertia. You hear it, perhaps, the movements of the building. Perhaps you can see it. Generally, trying to see the motion is very difficult because you have no reference. As long as you get rid of the twist, even the twist may not be that much of a visual issue anymore. But so you really can't see it moving. Now, can you hear it moving? Well, in this particular structure, you have very little frame action. Okay, you don't have beams and columns that are racking and the angle is changing, so you don't really have squeaky partitions. You have a little bit of flexural compression or extension at the edge. So it's very quiet in that sense. I mean, audible quiet. And then finally is the motions. And what we look at the ISO curves, which correct for both accelerations and period. Now the period's around 11 seconds, so it actually moves in a relatively gentle manner. Now, when you get down to the residential, it's really quite low. And I'm going to grab a number from memory. I think in a 10-year storm, it's around, I want to say 7 or 8 millig's. It's very, very low. It's a very quiet building. This is just using the inherent dampening of the building. I've been in the building. I've been up on level 160 when it's pretty blustery down at the base, and I couldn't feel it move. So it's a really pretty quiet building.
Let's go ahead and take your second question.
Could you
repeat it, please?
At the column junction, how do you cater for the ductility? Because the very thin connection of a flat plate with the column, and you use response reduction factor of 5 under earthquake. How do you cater for that? You ensure that when the actual maximum concern earthquake, yes, Jang, when maximum concern earthquake will come, your forces are going to be 5 times. How do you ensure there is no punching? Because then it will lose its vertical load. You have a flat plate with a column under earthquake. How do you ensure the ductility and there is no punching? Because you have used response reduction factor of 5.
Yeah, that's a good question about using the flat slab of structure. As you see on my presentation, we use the 250 millimeter thickness flat plate. And also, we use it as effective girder. So, in that case, we are very careful with the moments and unbalanced load, and also, as you mentioned, the punching. So, nowadays, we have excellent tool examine that one FEM like that. So after finding out that the exact result, if the punching shear is more than by concrete itself, we put the extra reinforcement or special stud boards for punching shear. Thank you.
My question is for William. William, is it right that when the building was in plan, in the wind tunnel analysis for Burj Khalifa, you took the intrinsic damping as 3%, and by end of it, when it went up, you realized there were problems, and there was a big problem while completing it. Just before you take that, my next question is to David. David, just your take on the statement that any of the efficient structural systems that you've shown can be made more efficient simply by adding damping. And my last question is for Professor Kim, which is just a short one, which is while using outriggers, at what levels did you find your at what stress levels did you get your concrete cracking, and did you notice that you had certain portions of your core wall cracking while the others were uncracked? Thank you.
To be fair for all people in the audience, I'm going to have to hold everyone to one question. So,
Okay, well, I'll take the question. Anyway, the damping we assume, there's always a big mystery when you start a project, what damping to assume. And so what we did is, because of the nature of this building, we looked at how much the energy was stored in different elements of the building, how much was stored in, if you went through a cycle of oscillation, how much energy was stored in elements which would have been uncracked versus flexural elements which would be cracked and the like. And we backed into a number of around 1.5%, and that's what we used in our calculations. And there have been measurements of the building, and we're measuring approximately that now.
Your comment about you can't make buildings more efficient by adding damping, I disagree with. Quite often you get into a position where buildings are being governed by its performance under the sort of its accelerations under the wind loading. And if you add in damping, either in the form of viscous dampers, then you can, or tune mass dampers, then you can make the building. Pardon? Yes. Well, it says that's if you're adding damping either by viscous dampers or by tune mass dampers, the viscous dampers can take energy out of the building, and we have looked and have applied to tall buildings. In New York, we just did it to improve the damping performance so that the accelerations were okay. But also, you have to remember that the wind loads in buildings are a function of the damping. So if you add in damping, such as viscous dampers, and you, instead of using 1.5%, you might have 2.5%, then you end up with a reduced wind load, which can actually improve the efficiency of the building.
Next question.
Hello, sir. I'm Kintan Shah. I'm a student. This is a general question for all of you. While designing tall buildings, earthquake is taken into consideration, but you never know nature's fury. So, is it considered that if a building falls, it falls according to us and not according to nature, by differing the strength of columns or core?
We don't know what we don't know. Okay, we're going to learn things in the future that we don't know today when we're designing our buildings. So what you have to do is you have to design your buildings so they forgive you, that they're ductile and they're strong and they're well tied together, so that if something happens in the future, which no one anticipates today, that the building will be able to redistribute the loads and handle the things. And so, good detailing, good practice goes a long way from, as far as what we think and what nature, what we do tremendous calculations to great accuracy about very vague knowledge. And so you have to be careful about getting lost in the numbers. You got to think about the systems.
So, my question was, if at all it falls, is care taken that it falls in the direction where the damage occurs is less?
No, I think if towers fall, they fall downwards, and therefore that is where the most damage would be. And we don't design for that. We try and design to stop them falling.
I've got a very innocent question. Is it really worth living in such a complicated way? Because I have to live on mercy of two people. One is on God, second is a structural engineer.
Could you repeat that question?
Sorry.
You stumped the board.
Yeah, my question was, is it really worth living in such a complex way? Because I like to believe on two people. One is God, second is a structural engineer.
Yeah, I mean...
Are we complicating too much?
If you don't want to believe in structural engineers, then you should live in a tent. Other than that, you're pretty much out of luck because, look up. You're believing in structural engineers. There's a nice grass roof on top.
My question is for Mr. Jong. Universally, the codes are skeptical about columns participating in lateral load resisting system, especially when there are flat plates. So in your analytical model, were they pinned or fixed with the slab? I mean, were they part of the lateral resisting system?
I think the question is directed at gravity columns participating as part of the lateral system.
Are the columns participating as part of the lateral system? The joining rising as part of the lateral system?
Yes, it's not easy part of to decide the flat slab participate for the lateral system or not. It depends on the structure engineer decide it. So if we put the flat slab as lateral system, so as you see in my presentation, it will add 60% of stiffness to the building, but we have to design according to that, put more reinforcement. Sometimes we put extra shear reinforcement for it, add also shear force also. So it is combined of the role of whole system.
So aren't we overruling the code which says that columns in flat plate shouldn't be part of the lateral resisting system?
Yes, it depends on the structure, what kind of system is. So the structure engineer must decide how to go.
Hi, I have a question which is a joint question to Mr. David Scott and Mr. William Baker. The kind of practices which Arup and SOM have are in some ways so starkly different from each other. And especially when you're talking about Arup and you're working with Daniel Libeskind or Reem Koolhaas and you're doing all kinds of weird structures. You know, if you look at CCTV tower in China and so on. What are the pressures you have? Because a lot of these architects are people who would say, I've made up my mind, don't bother me with facts. And if you can't give me the solution, change the structural engineer, don't change the architecture. As versus SOM, which, you know, I think that one of your colleagues had said that the form follows the performance. My question is really, where do you see the future of tall buildings going towards? And I'm seeing more and more that the architects are coming into play as versus, you know, when SOM ruled the roost starting from, you know, whatever, early 60s on, and now you're having more and more gymnastics in tall buildings. Where do you see it going?
Maybe I'll start and he can rebut. I think that the trend or the opportunities, as I said in my talk, is that engineers are becoming better at analyzing, contractors are becoming better at building, and therefore there is a renewed sort of willingness to try and look at doing some things that are different and better than before. And from my perspective, it's always works best when there is a strong collaboration with the architects and engineers and that they listen, so that the design that I showed you of the Leapskin project, for instance, was modified based on our input, and it wasn't saying we're going to do that. And where it falls down is when people don't listen, and that does sometimes happen for a greater vision. But I think that the to some extent the trend, I think, is being reversing, because people want buildings that are efficient and effective, and that doesn't mean to say that they are exactly the same as what we've done before, and that you're taking one building and copying it and making it taller. And I think that cities need and want a vibrant urban urban architecture, and they don't want this repetitious boxes everywhere. So I think there is a trend to do some interesting buildings. SOM have done some very interesting buildings, and that are not by any means simple, just square boxes.
Part of it is, I think, I think some of the exuberance you've seen lately is going to get kind of squashed by the financial crisis we're in. I think things will calm down a little bit because of that. But also, I think we're in a new paradigm where I think a lot of these shapes are coming from architects because they don't have any other good ideas, okay? It's just exercises in form, and I think it's up to the technical people, the engineers, who are, the sustainable people, the structural engineers, the mechanical engineers, to come up with good ideas that are technically sound that will change the way architecture looks. You look at Ken Yang's work this morning. It's about a sustainable. It's about a green thing that changes his architecture. It wasn't about just arbitrary form shaping. I think, I know Arup does a lot of research. We do a lot of research on trying to create new topologies or new reasons for a building looking different, but for a good reason, not just an arbitrary reason.
And unfortunately, due to time, I'm going to have to pull the session to a close. I know there's some more questions out there, and I would encourage you, when we're done with this, that please come up and talk to the speakers. We hope you are challenged and inspired with these discussions. Please join me in thanking our speakers.